British anti-tank guns stopped penetrating German armor. 2-pounder rounds began bouncing off new tanks. Field reports described shells failing at close range. Armored cars suddenly faced vehicles they could not stop. War Office procurement officers demanded immediate solutions. Designing a new gun required years of factory conversion. Britain did not have those years. Engineers examined radical ballistic experiments instead. One proposal appeared mechanically unusual: a gun barrel that squeezed the projectile smaller. Velocity would increase dramatically during exit. Penetration might double without a new weapon. The solution required only a strange muzzle device, a tapered steel tube attached to existing guns. This device became known as the Littlejohn Adapter. British ordnance planners evaluated anti-tank limitations. 2-pounder performance declined against thicker armor. Enemy vehicles increased frontal plate thickness during 1941. British factories continued producing existing 2-pounder guns. Replacing the system required large industrial conversion. Procurement committees requested temporary performance improvements. Design proposals focused on projectile velocity increases. Several engineers examined squeeze-bore ballistic theory. The concept reduced projectile diameter during barrel exit. Smaller diameter increased velocity and penetration efficiency. German engineers previously tested tapered bore artillery. British intelligence reviewed foreign squeeze-bore experiments. Adapting the principle to existing guns became attractive. Major Denny Burney examined engineering feasibility studies. Burney proposed a detachable tapered muzzle adapter. While the device required no permanent barrel modification, existing guns could accept the attachment externally. The adapter contained an internal tapered steel bore. The entrance diameter matched the original projectile diameter. The exit diameter narrowed significantly toward the muzzle. Special ammunition incorporated a deformable outer skirt. The projectile core remained hardened tungsten carbide. The outer jacket compressed while passing the taper. Compression reduced projectile diameter before muzzle exit. Reduced diameter increased sectional density after discharge. Higher velocity resulted from reduced aerodynamic resistance. Penetration improvements appeared theoretically significant. War Office committees approved prototype fabrication. Initial prototypes manufactured using high-grade alloy steel. Precision machining produced smooth internal taper surfaces. Manufacturing tolerances required careful dimensional control. Adapter threads matched the existing 2-pounder muzzle. Engineers designed locking collars preventing recoil, loosening. Prototype testing occurred at Shoebury-Ness Artillery Range. Early firing trials used experimental tungsten projectiles. Observers recorded muzzle velocity measurements carefully. Initial tests showed dramatic velocity increases. Standard 2-pounder velocity averaged around 800 meters. Squeeze bore firing exceeded 1,200 meters velocity. Armor plate penetration improved under controlled testing. 30mm armor plates failed under short-range impacts. Conventional ammunition previously struggled against similar targets. Range officers examined projectile stability after compression. Some rounds displayed yaw during longer flight paths. Accuracy results varied across early batches. Investigators attributed issues to inconsistent projectile skirts. Ammunition factories revised skirt metallurgy composition. Soft alloy skirts improved compression reliability. Subsequent firing cycles demonstrated better projectile alignment. Additional trials expanded testing to medium armor plates. 40mm armor occasionally penetrated under optimal angles. Testing committees considered operational deployment feasibility. Reports emphasized tungsten core dependency for penetration. Tungsten supply within Britain remained limited. Procurement authorities tracked global tungsten shipments carefully. Most tungsten arrived through vulnerable shipping routes. Strategic material allocation created bureaucratic friction. Some officials argued tungsten better suited aircraft tools. Others supported anti-tank ammunition prioritization. Supply ministries debated allocation during 1942 meetings. Limited tungsten availability constrained ammunition production planning. Adapter manufacturing continued despite resource uncertainty. Factories machined several hundred units during pilot production. Adapters received the designation Littlejohn Adapter. The name derived from Major Burney's nickname. Official documentation referenced the tapered bore attachment. Field units required training before operational use. Instruction manuals described attachment installation procedures. Soldiers mounted adapters directly onto muzzle threads. Locking collars secured the adapter during firing cycles. Maintenance schedules required frequent internal inspection. Taper surfaces accumulated residue after repeated discharge. Cleaning rods removed powder deposits from narrow sections. Armorers monitored taper wear after heavy firing. Excessive wear reduced compression efficiency gradually. Replacement schedules depended upon firing frequency. Transport crates carried spare adapters for field units. Ammunition packaging clearly marked squeeze bore rounds. Standard ammunition remained incompatible with installed adapters. Incorrect ammunition could damage the tapered bore. Training emphasized strict ammunition identification procedures. Operational units began receiving the system during 1943. Most installations occurred on armored car variants. The Daimler armored car carried the 2-pounder gun. Reconnaissance regiments favored improved armor penetration capability. Crews appreciated increased muzzle velocity performance. Field reports described improved results against light armored vehicles. However, tungsten ammunition remained scarce during campaigns. Logistics officers rationed squeeze bore rounds carefully. Standard ammunition continued dominating supply inventories. Combat engagements often reserved tungsten rounds for emergencies. Adapter removal allowed firing conventional ammunition again. Crew procedures required unscrewing the muzzle attachment first. Removing the adapter required protective gloves during operations. Metal surfaces heated significantly after repeated discharge. Operational manuals warned about thermal expansion effects. Excessive heat sometimes tightened adapter threads temporarily. Field armorers carried specialized removal tools accordingly. Maintenance inspections documented occasional thread damage. Improper installation sometimes caused misalignment problems. Misalignment reduced projectile stability dramatically. Investigators implemented additional alignment gauges during servicing. Inspection teams evaluated deployed units during field exercises. Data collected measured reliability across several regiments. Some units reported adapter cracking after extensive firing. Engineers studied stress distribution within tapered walls. Reinforcement modifications improved structural durability slightly. Production lines adopted revised wall thickness specifications. Even improved designs required careful firing discipline. Rapid firing accelerated internal taper erosion. Operational doctrine limited continuous firing sequences deliberately. Despite constraints, penetration performance remained valuable. Reconnaissance vehicles could challenge previously resistant armor. War Office reports documented tactical advantages occasionally. However, tungsten ammunition shortages persisted throughout deployment. Industrial planners considered alternate projectile materials. Steel core variants performed poorly in trials. Armor penetration dropped significantly with substitute metals. Research teams examined carbide composites unsuccessfully. None matched tungsten core ballistic performance. Consequently, ammunition allocation remained tightly controlled. Procurement offices balanced demands across multiple weapons. Aircraft machine tools also required tungsten carbide supplies. Strategic material boards managed competing wartime priorities. Littlejohn Adapter production continued through limited batches. Records indicate several thousand units manufactured eventually. Deployment remained restricted to specific reconnaissance formations. By late war, heavier anti-tank guns appeared. 6-pounder systems gradually replaced earlier weapons. Improved guns delivered greater penetration without adapters. Armored vehicle upgrades also introduced new armament. Operational reliance on squeeze bore systems declined. However, existing adapters remained issued where ammunition existed. Post-war assessments evaluated overall system effectiveness. Technical reports acknowledged clever engineering adaptation. However, reliance upon scarce tungsten limited scalability. A maintenance complexity also reduced widespread adoption prospects. Later anti-tank weapons eliminated squeeze bore necessity. Nonetheless, the adapter represented wartime engineering improvisation. British engineers exploited existing platforms creatively. Industrial limitations shaped unconventional mechanical solutions. Documentation preserved detailed design drawings and firing data. Modern historians examine the device within procurement archives. Recovered adapters survive in several military museums. Machining marks remain visible inside tapered bores. Inspection reveals the precise compression geometry clearly. The design illustrates practical squeeze bore implementation. Few armies attempted similar detachable adapters. The British solution avoided full barrel redesign. This reduced production disruption during wartime. Existing weapon stocks gained temporary performance improvement. Engineering committees considered the compromise acceptable. Despite constraints, the concept functioned mechanically. Field use confirmed theoretical ballistic principles. Material shortages ultimately restricted operational influence. Nevertheless, the Adapter remains historically distinctive.